Section 7.3 Trigonometric Methods. In this section, we are going to use trigonometric methods to find integrals both involving and not involving trigonometric functions. Powers of sine and cosine. We begin by considering a product of powers of sine and cosine. First of all, we review two useful identities. Cosine square equals 1/2 of 1 plus cosine 2x. Sine square x equals 1/2 of 1 minus cosine of 2x. They are sometimes called half-angle identities. When the power of cosine is even, such as 4 in this example, you can apply the half-angle identity. First of all, write cosine 4x as the square of cosine square, then using the half-angle identity for cosine square, squaring the result to obtain a formula that involves cosine square of 2x. The half-angle identity is applied once more time to obtain cosine 4x, and then we can find the integral. Now, you are asked to integrate a mixed product of cosine square x sine x. Remember that minus sine x is the derivative of cosine x. If we substitute u equals cosine x, then du equals minus sine x dx. The integral becomes minus the integral of u squared du. Using the power rule, and then convert the result back in terms of x to obtain minus 1/3 cosine cube x plus c. In this example, the integrand is a mixed product of cosine square x sine cube x. Since the power of sine x is odd, you can separate a factor of sine x from the rest of the integrand, so the remaining power of sine x is even. Use the identity cosine square x plus sine square x equals 1 to express everything in terms of cosine x. Since the power of sine x is odd, you can separate a factor of sine x from the rest of the integrand, so the remaining power of sine x is even. Use the identity cosine square x plus sine square x equals 1 to express everything but the term sine x dx in terms of cosine x. Substitute u equals cosine x, du equals minus sine x dx to convert the integrand into a polynomial in u, and integrate using the power rule. Trigonometric substitution. Trigonometric substitutions can also be useful for integrals that involve quadratic forms. We create 3 columns: the original function, the substitution, and the result after substitution. For the function square root of a squared minus x squared, by setting u for the function square root of a squared minus x squared, by setting x equals a sine theta for an acute angle theta, and using the identities cosine square equals 1 minus sine square, we obtain a cosine theta. Thus, the substitution x equals a sine theta eliminates the square root and convert the given integral into one involving only sine and cosine. For the function square root of x squared plus a squared, the substitution x equals a tangent of theta, we convert it to a. For the function square root of x squared plus a squared, the substitution x equals a tangent of theta, we convert it into a sec theta. If the function has the form square root of x squared minus a squared, we set x equals a sec theta to convert it into a tangent of theta. For these substitutions, we require that theta is between 0 and pi over 2. The process is illustrated in the following examples. First example, integrate 1 over square root of x squared plus 4. Let x be 2 tangent theta, then dx equals 2 sec square theta d theta. The initial integral becomes 1 over 2 sec theta multiplied 2 sec square theta d theta, or the integral of sec theta d theta. This is a basic integral. Use formula 9 to obtain log n of sec theta plus tangent theta plus c. Now, to write the result in terms of x, we set up a reference triangle with one leg of x and one leg of 2. Notice that for this triangle, x equals 2 tangent theta. The hypotenuse is square root of x squared plus 4, so sec theta plus tangent theta equals 1/2 of square root of x squared plus 4 plus 1/2 of x. Second example, integrate x over square root of 16 minus x squared. Let x be 4 sine theta, then dx equals 4 cosine theta d theta. Substituting in the initial integral, square root of 16 minus x squared becomes 4 cosine theta. X becomes 4 sine theta and dx becomes 4 cosine theta d theta. So the integral becomes 4 sine theta d theta. The result is minus 4 cosine theta plus c. Now to write the results in terms of x, we set up a reference triangle with one leg of x and hypotenuse of 4. Notice that for this triangle, x equals 4 sine theta. The other leg is square root of 16 minus x squared. So cosine of theta equals 1/4 of square root of 16 minus x squared. Third example, integrate x squared over square root of 5 minus x squared. Let x be square root of 5 sine theta, then dx equals square root of 5 cosine theta d theta. Substituting in the initial integral, square root of 5 minus x squared becomes square root of 5 cosine theta. X squared becomes 5 sine square theta, and dx becomes square root of 5 cosine theta d theta. So the integral becomes 5 sine square theta d theta. Using the half angle formula to convert sine square theta into 1/2 of 1 minus cosine theta. The result is 1/2 of theta minus 1/2 of sine 2 theta plus c. Note that sine 2 theta can be written as 2 sine theta cosine theta. Now to write the result in terms of x, we set up a reference triangle with one leg of x and hypotenuse of square root of 5. Notice that for this triangle, x equals square root of 5 sine theta. The other leg is square root of 5 minus x squared. So theta equals to the inverse sine of x over square root of 5. Sine theta equals x over square root of 5, and cosine theta equals square root of 5 minus x squared divided by square root of 5. In the next example, we prove that the integral of 1 over x squared plus x squared equals to 1 over a, the inverse tension of x over a plus c. Let x equal a tension theta, then dx equal a sec square theta d theta. The expression square x squared plus a squared can be written as square root of x squared plus a squared square. The initial integral is equal to 1 over a squared sec square theta multiplied by a sec square theta d theta, or 1 over a integral of d theta. The result is 1 over a theta plus c. Replacing theta by inverse tension of x over a to get the result in terms of x. Quadratic form integrals. Quadratic form integrals. An integral involving an expression of the form a square x squared. An integral involving an expression of the form ax squared plus bx plus c with ab not equal to 0 can often be evaluated by completing the square and making an appropriate substitution to convert it into one of the forms we have previously analyzed. For example, consider an expression of the form square root of x squared plus 3x minus 5. We can complete the square by adding and subtracting 9/4 from the expression in the square root. The result is square root of x plus 3/2 squared minus 29/4. Let u be x plus 3/2, then the expression becomes square root of u squared minus 29/4. This is the end of section 7.3. Thanks for watching.